Good morning, welcome to new lecture. Today I will review several examples regarding the equilibrium of rigid body and type of reactions. Let's look at the first problem. Assume we have this beam, this fixed support, and this beam is subjected to two concentrated load L over 2, L over 2. I want to find reactions here. This is fixed support, so I will have AY, AX, and MA. These are our reactions because fixed support in 2D space will have three reactions. Summation of forces in horizontal direction is equal to 0. From here I can write AX is equal to 0. Summation of forces in vertical direction is equal to 0. From here I can write AY minus P is equal to 0. So AY will be equal to P. Summation of moment respect to one point is equal to 0. For example, respect to fixed support is equal to 0. At point A, moment we have one reaction for support A. Counterclockwise I assume the direction, so it is positive, minus P times distance. This P times L over 2 wants to rotate this beam respect to point A clockwise, so negative P times L over 2. Again, P times L, it wants to rotate this beam respect to point A clockwise, so negative P times L is equal to 0. From here, MA, support reaction, will be PL plus PL over 2. That will be equal to 3PL divided by 2. Let's look at the next example. Assume we have simply supported beam. Simply supported beam, it means one support, it is hinge or pin support, another support, it is roller, subjected to one concentrated load, and the location of this concentrated load, from this side it is L over 3, and from the right side it is 2L over 3. So point A, point B, I want to find reactions. Again, this will be BY, one reaction for roller support, two reactions for hinge support. Again, we can write three equilibrium equations. So summation of forces in x direction is equal to 0. From here I can write AX is equal to 0. Summation of forces in y direction is equal to 0. From here I can write AY plus BY minus P is equal to 0. And summation of moment respect to one point, for example point A, is equal to 0. So AX and AY both, they will pass through point A, so they will not create any moment respect to point A. BY times distance perpendicular to the BY direction, it wants to rotate this beam respect to point A counterclockwise, so it is positive BY times L minus external load P times the distance respect to point A, L over 3. It wants to rotate this beam respect to point A clockwise, so negative is equal to 0. From here, BY will be equal to P over 3. And if we plug BY here, From this equation, I can find AY is equal to 2P over 3. Let's look at the next example. Next problem. We have beam and the support type, it is like this. Let's see what type of the support is this. This is beam, and here we have roller support. This beam is subjected to load P at midspan. We want to find reactions. Here this support, for example, point A, point B. Point B support is roller support, so we have one reaction, By. Support A, it is not fixed, it is not roller, it is not pin. So let's see how many reactions do we have here. You see here, point A can move in vertical direction, so there is no reaction in vertical direction, but it cannot move in the horizontal direction. So we have AX, and it cannot rotate. So we will have one moment reaction. I show that moment reaction, for example, in this direction, MA. Now, I can write equilibrium equation, summation of forces in horizontal direction is equal to 0. From here, I can write AX is equal to 0. Summation of forces in vertical direction is equal to 0. From here, Dy minus P is equal to 0, so Dy will be equal to P. Summation of moment respect to one point, for example, point B is equal to 0. In that case, P times L over 2, the distance respect to point B, it wants to rotate this beam counterclockwise, so positive P times L over 2 minus MA, it wants to rotate this beam respect to point B. In this direction I show it, I assume it is clockwise direction, so negative MA is equal to 0. From here, MA will be equal to PL over 2. So, let's look at to the next example. Next problem, we have beam. This beam we attach to the ground using two springs. One spring is here, another spring is here. Point A, point B. And the stiffness of each spring is K, and the K magnitude is known. It is 100 Newton per meter. From A to B, the distance it is 2 meters. From B to C, distance it is 1 meter. At point C, we apply force 13 Newton. Initially, this beam it is horizontal. After we apply force 13 Newton at point C, definitely this beam will rotate. This point C will move down. So, it will not remain horizontal anymore. We want to find the tilt angle. We want to see how much this beam will rotate. So, after we apply the load, this point B definitely will move down, point C will move down, point A will move up. And because beam initially it is a straight line and it is rigid beam, it means we neglect the deformation of the beam, it will remain a straight line, so it will rotate like this blue line. We want to find tilt angle to see how much this beam will rotate. So we see from the problem point B will move down to the point B prime, point C to the point C prime, and point A will move up to the point A prime. So once point B will move down, this spring will apply force upward because it wants to return point B to the initial position. And here spring will apply force Fa downward because it moves up, and this force it wants to return the point A to the initial location. So let's see what can I write using equilibrium equation. If I look at to the beam, now here I have force Fb upward, force Fa downward, force external load 30 Newton, and I know this is 2 meter and this is 1 meter. Summation of forces in vertical direction is equal to 0. From there, I can write Fb minus Fa minus 30 is equal to 0. Fb upward positive minus Fa minus 30 is equal to 0. Summation of moment respect to one point, for example point A, is equal to 0. I can write 30 times 3, it wants to rotate beam counterclockwise respect to point A, so it is positive, minus Fb times 2, it wants to rotate this beam respect to point A clockwise, so negative, is equal to 0. Because I'm writing equilibrium of moment respect to point A, this Fa passes through that point and will not create any moment respect to that point. So from here, Fb will be 45 Newton. If we plug here, we can find Fa is equal to 15 Newton. So now I know the magnitude of Fb will be 45 Newton. The magnitude of Fa will be 15 Newton. I know force in spring is equal to stiffness of spring times the deformation of spring. So Fa is equal to K, stiffness of spring, times Xa. From here, I can write 15 is equal to 100 Xa, and from here I can find Xa is equal to 0.15 meter. In similar way, Fb is equal to K times Xb, because Fb is 45 Newton is equal to 100 times Xb. From here I can write Xb is equal to 0.45 meters. Now, I found Xb, I found Xa. Let's look at the beam. Beam initially was one horizontal line. Point A will move up 0.15 meter. Point B will move down 0.45 meter. So this beam initially was a straight line. Now it will rotate like this. So In this triangle, if I draw one straight line from here, I show with dashed line. You see this triangle. In this triangle, from point A to point B, it is 2 meters. This moves up 0.15. So these two lines, they are parallel. So this height will be 0.15 meters. So entire height from here to here, entire this distance will be 0.15 plus 0.45. That will be equal to 0.6 meters. So this angle theta, I can write sine of theta is equal to this length, which is 0.6 meters from here to here. This is 0.6 meters divided by this length. This length AB initially was 2 meters. Now after rotation, from this point to this point, again 2 meters from this point to this point, because this rod will rotate. So from A to B will remain again 2 meters. From here I can find the theta. Theta will be inverse sine of 0.6 divided by 2. From there, if you calculate theta, theta will be equal to 17.5 degrees. Pay attention, AB initially was 2 meters the distance. After rotation, because this beam rotates again from A to B, will be 2 meters. Now for next session, try to solve this problem as your homework problem. Very similar problem. You have beam again with 2 springs. Almost everything is the same. You have this beam. You have 2 springs. The stiffness of the spring here is K, point A, point B, and this force here it is 30 Newton. The distance from here to here it is 2 meters from A to B. From B to C it is 1 meter. Problem statement says determine the stiffness K. We want to find the stiffness of these springs K. Determine the stiffness K of each spring so that the 30 Newton, this force, causes the bar to tip. Theta is equal to 15 degrees. So now find K so that after applying this load, this beam will rotate or will tilt equal to 15 degrees. This is your homework problem for next session. Let's solve another problem. Next problem, we have one rod using one pin support. I attach this rod to the ground. Here we have one spring. The stiffness of the spring, it is equal to 60 Newton per meter, point A, point B. Initially this is in vertical direction. Then I apply moment at point A. With rand, for example, I take point A and I rotate and I apply moment 50 Newton meter. 50 Newton meter. The weight for this rod, or the mass of this rod, it is 10 kilogram. After I apply this moment, I want to find the theta for equilibrium. Initially it is in vertical direction. After I apply that moment, that AB rod will rotate like this, and we will have elongation in a spring definitely. So I want to find this angle, theta. This rod or column length initially it is 2 meters. So initially it is in vertical direction. After I apply this moment, it will rotate. The rotation angle is theta. I don't know how much that theta, but I want to find it. I apply here the moment 50 Newton meters. This column or rod has a mass of 10 kilogram. So here, after rotation, we will have 10 times 9.81 mass times gravity. It will be weight, and weight will be the centroid of the rod, and it will be downward. So let's write equilibrium of forces, and using equilibrium of forces I can find the theta. Because initially this is on stretch spring, after I apply moment and deformation theta, we will have elongation here. If this length it is, initially it is 2 meters, after rotation is 2 meters, will remain the same length, and this is theta. This elongation will be 2 sine theta. From here to here will be 2 sine theta. So elongation here in this spring after rotation, because this length it is 2 meters, elongation will be 2 sine theta. Spring stiffness is 60. Stiffness of spring times elongation will give us force this spring applies in order to return point B prime to initial position. So this force FB will be stiffness of spring times elongation delta. That will be 60 times 2 sine theta. It will be 120 sine theta. From point A to center of here, point C, the length is 1 meter. So the position of this in the horizontal direction, it will be 1 sine theta. So if I write summation of moment respect to point A, and I put that equal to 0 in order to satisfy equilibrium, the summation of moment respect to this point should be equal to 0. I will have 50 moment I'm applying, that is clockwise, so negative, plus this force times distance up to point A. Again, it wants to rotate this column clockwise, so negative, minus 10 times 9.81. This will be weight or force times the distance will be 1 sine theta plus force times distance. It wants to rotate this column respect to point A counterclockwise, so positive. Positive force, which is 120 sine theta times distance. The distance initially was 2 meters. After rotation, this distance will be 2 times cosine theta. So that length now it is 2 cosine theta. So force times distance will be 2 cosine theta is equal to 0. This is one equation in terms of theta. If you calculate theta, you can put in calculator or Excel with goal seek. Easily you can find theta. You will end up theta is equal to 24.6 degrees. So once theta is equal to 24.6 degrees, this system will be in equilibrium and we will not have any motion. Pay attention, initially this length or this height it is 2 meters. But after deformation, this point B will move in the horizontal direction and vertical direction like this. If this is 2 meters, after deformation, if this is point B, we'll move to point B prime. This will be 2 sine theta. If this is theta, it will move in vertical direction as well. This height will be 2 cosine theta. And this distance in vertical direction will be initial height 2 minus 2 cosine theta. So force now is here. If I take moment respect to here, force times distance, which is perpendicular to the force direction, will be 2 cosine theta. Pay attention to that point. Let's look at to the next example. Next problem, we have one electromagnetic switch. The electromagnetic switch detail is like this. Here we have one spring. The stiffness of that spring is K. Here I have another spring. Again, the stiffness of this spring is K. Point A, point B, point C. Here there is a gap. The gap is 10 millimeters. Once I want to close the switch, I should apply force at point C, F. If I apply force F here, this will rotate and it will close the gap. So if I apply force here, this AC beam will rotate and it will close the gap. These distances are given 50 millimeter, 50 millimeter. Problem statement says K is 5 Newton per meter. And this is one detail of electromagnetic switch, and reality it is similar to this. Determine the smallest force. Determine the smallest force means the magnitude of this force. To close the gap at point C, so we want to close this gap at point C. How much? What is the magnitude of the smallest force I should apply at point C? Let's see. Draw free body diagram. Here I want to find force F. I want to find the magnitude. If I apply force F, point B will move down. So we will have one force upward here. It is FB. And point A will move up. So we will have another force downward in inverse direction, FA. And this is 50 millimeters. Point A, point B, point C. If I write summation of forces in vertical direction equal to 0, I can write FB minus FA minus F is equal to 0. If I take moment respect to point, for example, A equal to 0, summation of moment respect to point A is equal to 0. I can write FB times 50 millimeter. It wants to rotate this beam counterclockwise positive minus F times 100 clockwise negative. From here, FB magnitude will be 2F, and if I plug this FB here, FA magnitude will be equal to F. So now I know if I apply F here, internal force inside of the spring, it will be 2F. Internal force at point A inside of the spring, it will be equal to F. I found that. So, now if I look at to the same free body diagram, F here, force upward 2F, force downward F, point A, point B, point C. And this point B will move down to the point B prime, this point A will move up to point A prime, and this will rotate like this. We want to close this gap, so this distance is known. We want close to 10 millimeter. We want close 10 millimeter. If this is XA, this is XB, look at to this triangle. If I draw one horizontal line here, now in this triangle, from here to here will be 10 plus XA. You see this is XA. I draw horizontal line, so this will be XA from here to here. This distance will be 10 plus XA. And from here to here, this distance will be XB plus XA. So, if I write similar triangle relation, I can write XB plus XA. It means from here to here, this height, divided by from here to here, 10 plus XA should be equal to, this is 50, 50 divided by, from here to here it is 100, by 100. From here I can write, instead of XB, I can put FB divided by K. FB is 2F divided by K plus, instead of XA, I can put the internal force here, which is F divided by K, so it will be F divided by K, divided by 10 plus XA, again force inside of that spring at point A, divided by K is equal to 50 and 100, they will cancel, this will be 1 over 2. From here I can write, if I add this will be K, this will be 3F, this will be 10 plus F over K is equal to 1 over 2. From here I can write 6F over K, this multiplied to this is equal to this multiplied to 1 is equal to 10 plus F over K. If I take this f over k to other side, it will be 5f over k is equal to 10. So, finally, I reach to the 5f over k is equal to 10 millimeter. What is the k? K it is, the magnitude of k is given. The magnitude of k is 5 Newton per meter. The magnitude of this k is given. It is 5 Newton per meter. So I can write this here, 5f. Instead of k, I can put 5f divided by k, it is 5 Newton per meter, is equal to 10 millimeter. If I convert millimeter to the meter, this will be, let's see, let's see everything is right. So 5f over k is equal to the 10. So this will be 5f divided by 5 is equal 10 millimeter. 10 millimeter will be 0.01 meter. That from here f will be equal to this 5 and this 5. They will cancel each other. It will be 0.01 Newton, or that is equal to 10 millinewton. So F will be force in order to close this gap. It will be 0.01 Newton or 10 millinewton. Let's see, after you review this problem and you digest it and you understood the concept, try to solve similar problem. The similar problem, it is your homework problem. Let's see. Again, you have the same electromagnetic switch, so the problem statement is the same, but this time we don't know the K. So the K magnitude, it is unknown. It says determine the maximum K. We want to find maximum K so that the contact, it means this 10 millimeter gap, closes when force developed is equal to 0.5 Newton. So in next step you will solve as a homework problem. We don't know the K, stiffness of this spring, but you will find the K so that if I apply force at point C equal to 0.5 Newton, I will close this gap. Whenever I apply 0.5 Newton, this point C will touch barely point C prime, and this will move exactly 10 millimeters. So what is the K? This is problem statement. Another problem, again it is your homework problem. You will think about that and you will solve it, and then I will review that problem. You have this rod. Or beam. Here point A, rotation angle is theta, and here you have a spring. The unstretched length of the spring, it is 2 feet. The stiffness of the spring K, it is 50 pounds per feet. We have one weight hanging here, it is 200 pounds, and the length for this beam is 6 feet. So the length for this beam AB, it is 6 feet. I'm hanging one weight at mid-span, it is 200 pounds. At point B we have one spring, unstretched length of this spring it is 2 feet, but after I apply this load it will rotate and we will have elongation in the spring. The stiffness of the spring it is 50 pounds per feet. The rod supports a weight of 200 pounds and is pinned at its end A. Okay. If it is also subjected to moment at point A equal to 100 pound feet, determine the angle theta for equilibrium. The spring has unstretched length of 2 feet and stiffness of 50 pound per feet. So unstretched length of the spring it is 2 feet. After elongation definitely we will have longer spring. The stiffness of the spring it is 50 pound per feet. I am hanging one weight here, it is 200 pound. At the same time I am applying moment, clockwise moment at point A, it is 100 pound per feet. You see one end of this beam is pinned at point A, another end we will attach to the spring. The length for this beam it is 6 feet. I want you find the theta for equilibrium. Think about that and try to solve it. Regardless your solution is right or wrong, I will review and I will solve, so you can compare your solution. Thank you so much for watching this lecture. See you next session. Bye bye.